In our last video, we started looking at the engineering design process. We learned what a design process is, we learned how to define the problem, and we learned some techniques for generating concepts. In this video, we're going to pick up right where we left off and find out how we can turn these ideas into a real working plan of action. Step 3 of the design process is to develop a solution. At this stage, the designer is going to turn the concept chosen in Step 2 into an actionable plan. They create detailed technical drawings and CAD models of their design. Along the way, they have to think critically and fill in a lot of blanks about their idea. They have to define the specific attributes of the solution, such as its size and shape, with specific dimensions. What parts and pieces make up the design? How will they fit together? And how will they stay together? What materials will it be made of? What kind of coatings or surface finishes will it have? This is all information that is usually missing from the thumbnail sketches made during brainstorming. But it all has to be figured out during Step 3 before the design can be built. In Step 3, the crude thumbnail sketches made in Step 2 are developed into technical drawings. These are drawings that communicate the details of a design with a high level of precision. This includes information such as size, shape, and material, the appearance of the design, and any relevant assembly details. Technical drawings may be made by hand, on the computer, or both, depending on the project. There are many different types of technical drawings with different purposes. We'll learn a lot about the different types later in the course, but let's take a quick look at some of the types of drawings a designer might create during Step 3. Pictorial drawings are drawings that sort of look like pictures. They show objects in 3D, the way we actually perceive them in real life. These include drawings like isometrics, obliques, which may be drawn in cabinet or in cavalier, and perspectives, which may be drawn in 1-point, 2-point, or 3-point perspective. Each of these types of pictorial drawings has its own pros and cons. Depending on the project, you might select one over another. They're great for communicating the concept behind a design, but are not always the best for communicating technical details needed for constructing the design. For that, we usually use orthographic drawings. Orthographic drawings show an object in a series of two-dimensional views. This is a little less realistic looking than a pictorial drawing, but it makes it easier to communicate technical details needed for manufacturing, such as dimensions and assembly details. Sometimes the standard orthographic views can't communicate everything needed to make a part or a product, and additional special drawing views are added, like auxiliary views, detail views, or section views, which may include half sections, full sections, offset sections, or several others. Technical drawing is a language. It's filled with terminology and techniques that take time to learn. But if drawings are made clearly and correctly, they can take an idea from your head and communicate it to others with precise detail. We'll study the different types of technical drawings in much greater detail in the future. To keep it simple, we can break technical drawings into two groups based on their essential function. Why are you making the drawing? Who are you trying to communicate with? You may decide that you need to make a concept drawing. This is a drawing used to communicate the general idea of a design. These are usually pictorial drawings, but not always, and they are most useful for communicating with the clients and customers, who may not have the technical background needed to interpret complex drawings. Let's look at a few examples of concept drawings. This concept is drawn as a pictorial, specifically a 2-point perspective. It doesn't use color and does not indicate info about measurements or materials that would be needed to build this design, but it does communicate the general concept. This concept is also drawn in 2-point perspective. It uses color to enhance the visual understanding of the design. Here's an example of a concept drawing that is drawn as an orthographic instead of a pictorial. It still lacks the technical information needed to build the house, but it is useful for someone who wants to better understand the details of the design. Here's another orthographic used in a concept drawing. It communicates the general idea of the design. It would allow a client to understand the design and approve it for building, but a lot more information would be needed to bring this design to life. This example uses an orthographic drawing as well as 2 pictorial drawings to communicate the concept. And while it does include a lot of annotations that help someone understand the design, it's still not enough information to build the design. And the purpose of this drawing is still to communicate the concept. Concept drawings are very useful for certain situations, but another type of drawing that might need to be made during step 3 is a working drawing. Working drawings are drawings used to communicate technical details to the people that will build a design. They're less about looking good on paper and more about being sharp, clear, and showing a lot of technical detail. These are usually orthographic drawings, but not always. They usually do not use color, but sometimes they might, and they're best used for communicating design specifications with the manufacturer. Let's see a few examples. This is a drawing that might be included in a set of construction blueprints. It identifies what materials are used and how those materials come together in the design. This drawing also points out specific building materials. This drawing includes all of the dimensions, materials, and annotations needed to manufacture this bicycle rack. This is a good example of when pictorial drawings might be used in a working drawing to help communicate certain details, in this case the assembly details shown at the top of the page. Working drawings are probably not what the client wants to see. They can be difficult to read and understand for someone that doesn't speak the language of technical drawing, but builders and manufacturers are well versed in reading technical drawings, and these are the people that need to understand your design in order to make it real. CAD models are very useful tools for designers working on developing a solution. CAD stands for Computer-Aided Design. It has many advantages over hand drawings. It allows for easy collaboration and sharing. CAD models can be used to create drawings, assemblies, and animations quickly and easily. CAD models can quickly be brought to life with 3D printing and CNC technology. A drawback is that it requires specialized software and training. CAD programs can be expensive, and in certain situations, creating drawings by hand can be faster and nicer looking than CAD drawings. A lot of important work goes on during step 3. This is when the designer must do the difficult thinking that will prevent big problems later in the process. Before you can move on from step 3, ask yourself, have you turned your concept into a plan that can be built? Have you created detailed technical drawings to share with your clients and builders? Have you figured out all important aspects of the design? Is there a practical way to build the design? Will this solution solve the problem? If the answer is no, return to an earlier step to make some changes. This might mean going back to redefine the problem or to generate new concepts. Most of the time, it means stepping back into step 3 to rethink the specific details of the design and finding a way to make it work. If the answers to these questions is yes, then you're ready to move on to step 4. Step 4 of the design process is to construct and test your design. During this step, the designer takes the plan they created during step 3 and they turn it into a 3-dimensional reality. This might be done with a mock-up, a model, or a prototype. At this step in the process, the prototype will need to be tested, so the designer needs to plan a whole battery of tests for the product. They collect lots of data during the testing and analyze the data to see what it says. People use a few different terms when it comes time to bring a design into 3-dimensional existence. So let's see if we can tell the difference. A mock-up generally refers to a quick and dirty assembly. These are sort of like the 3D equivalent of a sketch. They're made fast, usually from cheap, quick materials such as cardboard or duct tape. They're a good way to quickly communicate a concept in 3D without laboring over the finer details. A model is a bit more refined. Models are scaled 3D representations. They have totally accurate proportions to the real product, though they may be made at a miniature size, like with a building, or oversized to better show the details of a small product. They are normally made to be more visual than functional, but they give us a good sense of what the real 3D object will look like. High-quality models will imitate details like colors, textures, patterns, and materials. A prototype is the first complete working version of the product. It is the product designed during Step 3. Prototypes are made to be tested, so they must be accurate and true to the design in every way. If design changes are made at this stage, then the designer should go back to the technical drawings and CAD models made during Step 3 and revise them to show the changes. Traditionally, students studying design had to learn how to make accurate models by hand. This took a very specialized set of skills. They would have to become masters at creating visually accurate 3D models using simple tools like X-Acto knives, glue, foam, and wood. With practice, they could make scale models that look just like the real thing. Some professionals still make models this way, but the process is incredibly time-consuming. Today, model making has shifted almost entirely towards rapid prototyping technology. The term rapid prototyping refers to a set of technologies that create physical 3D parts directly from digital CAD models. This includes devices such as 3D printers and CNC machines. Rapid prototyping is a bit of a misnomer, since very often the items made through rapid prototyping are actually visual models, not functional prototypes. It's also a bit of a misnomer because it isn't always very rapid. 3D printing technology has improved dramatically in just a few short years, but jobs like this one can still take many hours to complete. However, the machine can do this work independently, freeing up the designer to work on other projects, maybe take a nap, or whatever else they need to do. Different types of 3D printers can build items from different materials, including many kinds of plastic, metal, concrete, and even chocolate. CNC technology, such as a computer-controlled laser, can be used to cut intricate shapes in flat material. Pieces can be stacked together to make three-dimensional models. Or designs might be reimagined to be made from cut-out pieces of flat stock. CNC simply stands for Computer Numeric Control and refers to any machine that can be controlled by a computer. This image shows a CNC mill, which is used to cut out parts from metal. Other CNC machines might be used to carve wood or cut out shapes with superhot plasma or high-pressure water. Rapid prototyping technology allows designers to spend more time working on designs and less time trying to figure out how to build them, resulting in better designed products. Some of these technologies can create complex shapes and geometries that simply were not possible before. The most exciting thing is that rapid prototyping technology is still in its infancy, and we will get to watch it grow up within our lifetimes. Let's check in with the IDEO design team and see how they handle the prototyping phase with the shopping cart challenge.
Back at the shop, it is 6 o'clock, and the 4 mock-ups are ready for showing.
Baskets also can be, if you think you will have more volume, baskets can be put in.
A modular shopping cart you pile hand baskets onto. A high-tech cart that gets you through the traffic jam at checkout.
That you could mount a scanner on the shopping cart so that you as the customer, as you pull it off the shelf, would scan each item.
One that's built around child safety, and another that lets shoppers talk to the supermarket staff remotely.
Yeah, where can I find a yogurt?
The yogurt's over in the dairy section.
But the adults, again, decide more work needs to be done before the mock-ups can be combined into one last prototype.
Why don't we have all the carts come up here for a second?
I think you take a piece of each one of these ideas and kind of back it off a little bit and then put it in the,
right.
design.
Once a prototype has been built, it needs to be tested. Way back when the design brief was written, the criteria for success of a solution was defined. Now, the prototype needs to be tested against every one of those criteria. The designer must test the prototype for things like usability, durability, safety, consumer reactions, and many other factors. The goal of testing a prototype isn't just to find out if it can work once, but to find its limits. If it works once, will it work 50 times? 100? 1,000? If it eventually wears out and stops working, why? What wears out first? Under what conditions will the product fail? What happens if it gets wet? What about if it gets hot or cold? The point of testing the prototype is to figure out every imaginable way that the product could fail in order to determine how it could be improved. Whenever possible, the product should be given to the target consumer to test. If the product is designed for kids, give it to some kids. They'll put the product through more rigorous testing than could possibly be designed in a lab. If the product is designed for wheelchair users, it needs to be tested by wheelchair users. If the target consumer is a professional athlete, then the product should be tested by a professional athlete. Their reactions should be recorded and taken seriously. The designer should collect extensive data during the testing in order to fully understand the capabilities of the design, to measure improvement through multiple iterations, and to help figure out how the design can be improved. Before moving on from step 4, ask yourself, does the prototype work as expected? Have your technical drawings and CAD models been updated to reflect any design changes? And has test data been collected and organized? If the answer to these questions is no, you should return to an earlier step in the design process to make some corrections to your design. If the answer is yes, then you're ready to move on to step 5. It would be miraculous if a design team reached the end of step 4 without the need for major revisions. That's how the design process works. If the first model indicates a flaw in the design, return to an earlier step, correct the issue, and then move forward again. If the initial prototype has trouble during testing, diagnose the problem, return to an earlier step, and make some changes. Designers will often cycle through steps 3 and 4 many times, making many iterations of a design before they make a fully successful prototype.